Okay, so today's the last day of the class, so I'm happy you finished this theorem today. Okay. Yeah, last time I think I left out with one point that I want to say. So I think so here this is a group. Yeah. So here I think yeah. So what is mean here is that if you have this curve, right? So this curve like a space point at x naught, and then this x naught tilde is in the pre-image of this x naught under the current projection. And then this is the curve that's downstairs, and then we tell the group action. I think what it means, what's going on here is that you have the unique lifting of this curve to another curve, gamma r tilde. And when you do that, so there is actually a endpoint, right? So when you say this r acting on this x naught tilde, is actually it maps the action of this one. This one acting on this point basically send this point to this endpoint. Okay. So this is the inner point, this is the endpoint. Yeah. So that's exactly the same thing as I think we have another curve like here, right? And we have this curve acting on this one because we showed last time that these two lifts are the same. Okay. So that's complete the proof. Okay. Okay. So yeah. So that's okay. So let's do next. Okay. Okay, so I think go. Oh shoot. Okay. 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 So there is a corollary. Okay. So I'll stay and prove the corollary. Okay. So so part B. I won't state part. So there is part C and part D in this theorem. So I won't prove. Maybe I will just say what part C is, but I won't say what part D is about. Yeah, part D is about like the smooth version of this theorem, and then yeah, smooth version, and then part C is part C is basically says if this x tilde is a topological manifold, and then this x is a topological manifold of the same dimension. Okay. 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 Maybe I'll prove it as I need. Okay. I'll prove this part C and part D if I need it. Okay. Okay. So let's just save it for the future. Okay. Let's just save it for the future. Okay. Okay. So now so corollary 10.4.7. Okay, so now let X be a connected, locally symmetrical and locally compact Hausdorff space. Symmetrically connected. Locally compact. Hausdorff space. And then let X now be X. Your point is X. And then let gamma be a subgroup of this pi 1 X naught. So this is a group gamma. And then be a subgroup of pi 1 of X naught. Okay, then up to equivalence of covering spaces. Of covering spaces there is a unique connected covering space. Okay, so there is a unique connected covering space. Okay, covering space gamma hat from this X hat to X such that for some point X naught hat in this vertical gamma inverse of X naught hat, yeah, such that for some point X naught hat in this the vertical gamma inverse of X naught. Okay, so we have that this gamma push forward map from this pi 1 of X hat based at X naught hat to pi 1 of X naught. Okay, maps a pi 1 of X hat of X naught hat isomorphically onto gamma. Okay, isomorphically onto gamma. Okay. So in fact, okay, so if this gamma, vertical gamma from X tilde to X is the universal covering space. Okay, so it's the universal covering space then okay, so maybe I'll just write it here. So then we have the commutative diagram. Okay, so here we have this x student. Okay, and then this is the projection by gamma to this x, and then this is a I think this. Okay, so this is a quotient map by this group gamma to this quotient space. Okay, which is equal to gamma x quotient by the group gamma relation. Group relation gamma, and then this is the map. Gamma hat. Okay. Okay, so so that's the same picture that we proved last time. Okay. Okay, so here we identify this pi 1 of x naught that contains this subgroup gamma with deck of gamma, vertical gamma. Okay. Okay, moreover, so, okay, let's just, because the red part is about the smooth case, so let's just focus ourselves on this topological part. Okay. 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 So here, this axis are connected locally simple and locally compact. Okay, subgroup of pi 1. Okay. I think we are in the same setting. Okay. And then beside we have this okay, we have the commutative diagram. Oh, yeah. Oh, okay, so there's a unique connected coordinate space. Such that for each point, for some point x dot hat. Okay, this pi 1, this, okay. Okay. Sorry, it's, yeah. It's not exactly the same setting, but yeah, it's, okay, yeah, we'll see, okay. Okay, so for the proof, okay, so for the proof, okay, so the proof is, so this follows okay, so this follows immediately from, so theorem 10.3.3. Okay, I'll state them later. I'll state them later. Okay. Okay, which is the existence of the universal cover. Okay, yeah. So this is the this is the existence of the universal cover. Okay. Wait, can you guys see here? Okay. Okay. Yeah. So this is the existence of universal cover. So yeah, existence of the universal cover. Okay, and then and theorem 10.4.6. Okay, so theorem 10.4.6, which is the construction of a covering from a. Oh, okay. So the construction of a covering. Okay, so let's avoid collision. Okay. From a properly discontinuous free group action. Okay. Free group action. Okay. Okay, and proposition 10.2.9. Okay, which is equivalence of. Okay, so which is equivalence of coverings with the same image image fundamental group. Okay, so sorry, can't avoid. Yeah. So, yeah. So with the same. Image fundamental group. Yeah, already here. Sorry, it's a little bit correction. Okay, yeah. Okay, so let's see. Okay, so okay, so let's see. Okay, let's try to let's see why this is true. Okay, so this follows immediately from theorem 10.3.3, existence of the universal cover. Okay, so 10.3.3. Let me check. Okay, so 10.3.3 says that every connected, locally similarly connected topological space X has a universal covering space. Okay. So let's see. Okay, so here it says that there is a unique connected covering space, right? Yeah, such as this is true. So okay, so yeah, so this X is connected. Okay,